Thank you. Our next speaker is Dr. Willehmijn Appels from Lethbridge College. Hailing from the Netherlands, Dr. Appels is a hydrologist, soil physicist trained at Wageningen University. I'm sure I'm pronouncing that wrong. I apologize. She currently is the Mueller Applied Research Chair in Irrigation Science at Lethbridge College. The Mueller Group investigates how new scientific findings can be translated into practical applications for producers in the irrigated agriculture sector of southern Alberta. The group's research program is shaped in close collaboration with local industry and government partners. Current projects include field and lab studies and water and nutrient management with subsurface drip irrigation systems and field and model studies of the opportunities for precision irrigation strategies in complex landscapes. Thank you.
Well, thanks for the introduction and thanks for having me. I was reminiscing earlier at lunch that this is the first time that I'm speaking at an irrigation conference in Lethbridge. So this is really exciting. Our research at the college in the irrigation group is mostly driven by an ongoing quest for increasing efficiency. So whenever I do this type of talk outside of southern Alberta, I remind people that in our region, over the course of a summer, water is a finite resource, especially if it doesn't rain. We get a certain amount of snowmelt, we can capture some of it, and that's what there is. That's what we can use to grow crops. So if we want to continue irrigating and growing high-value products, we need to make the most of what we have. And if we want to increase acreages of potatoes or, grow even better potatoes, we'll need to be smarter about how we use what we've been given. The magic word in all this is precision irrigation. And precision irrigation is more than only variable rate irrigation. So yes, we look at how we can distribute water in different ways throughout the landscape, but we also look at how can we improve the timing of irrigation applications, or how can we play with where and how much water we deliver to a particular plant or a particular row of plants at a time. Our research group does field studies, lab studies, and simulation studies, so computer modeling. And the main research questions are, what is the potential in southern Alberta to increase on-farm water use efficiency? And how can we use new technology and new management strategies into working farm models? Today, I'll take you on a virtual tour of some of our projects. Starting in Lethbridge, we'll go to Colehurst before switching out east and stopping near Chin, Tabor, Vauxhall, and the Bow Island area. And what I'd like you to take away from this talk is that precision irrigation or variable rate irrigation or any type of advanced irrigation will require monitoring and an understanding of why we have variability in a field. I'd also like you to take away that there is still room to do more with less, and that we live in exciting times. Someone mentioned that agriculture wasn't sexy. When I went to university, irrigation was not sexy at all. And so maybe now I'm reaching the age at which it's interesting, or maybe irrigation has actually become a little bit more interesting. So, project one is not an outdoor project. 2 years ago, when I was worried what my staff would do during the winter, we built 3 indoor play sets. And so we built 3 large boxes, 3 by 6 meters, with a root zone of 90 centimeters deep. And we scooped in some local soils, loamy sand, a clay loam, and a silty clay loam from the Coaldale area. And we put in subsurface drip systems. This was in collaboration mostly with Southern Irrigation. And we wanted to test, can we describe the patterns of water and water distribution that evolve around drippers? Can we use these drippers and these lines to grow a row crop or a field crop? And what are the best management strategies? So subsurface drip irrigation, you have a line with a passive emitter, you pressurize the line, and water will move out of each emitter at a very slow rate. It goes directly into the root zone. So in the second photo, you see a little black cross, and above that you see dark soil followed by light soil. That's your wetting front above an emitter. Now, depending on the soil type, the way in which the soil around an emitter wets up has a different shape, and there's also a different size to it. So the questions here are, how big is that size, depending on your application size and your soil type? Can we play with the shape of this wetted area? Can we make it wider instead of larger? And what are management strategies or schedules if we want to grow a row crop or a field crop with this type of irrigation? So we determined the height and width of these wetted volumes by placing soil moisture sensors all around the emitters in these boxes. Here you see 3 panels that have the height, the width, and the width divided by the height for one of these soil types for events of different duration. So what you see is that if you apply a larger event, then logically the size of your wetted area increases. Your height goes up, your width goes up. Your width increases slower than your height, and therefore the ratio between the two becomes smaller. So you get, the longer you irrigate, the more oval with the long axis down, the shape of that wetted area becomes. What you can also see when you look at the middle panel, the W, is that you get a width that's at maximum for a 7-hour application, 50 centimeters or so. Now, if you think of a subsurface drip irrigation system that often comes with a recommendation to place your lines at 1 meter distance of each other, that has emitter spacings of anywhere between 40 to 60 to 70 centimeters, then that width by itself is not always enough to make connecting wetted areas in your entire field. You have one bulb, and then at your next emitter you have another bulb, but you don't have a distributed wet area. So that could be problematic. What we can show, though, we grew alfalfa in these boxes, is that if you apply multiple events, just every day, steady, small events, that by doing that and by providing just a little more water than the crop needs, that you can move that water further and further outside. So on the left, you see the moisture at 10 centimeters below the surface. So it's a horizontal cross-section. The black line is the drip line. The 2 crosses are the emitters. And on the right, you see a vertical cross-section, so the depth of the soil. And you should imagine that the drip line moving in and out of the screen at the location of that cross. So in 2 out of the 3 soils, over a longer period of time, we're covering almost the entire width between the drip lines. There's a little bit of a drier area right at the surface where there's some evaporation and just not enough capillary movement to push the water outside. Whereas in the top figure, so the clay loam soil, there's a clear separation between a dry area sort of straight in the middle of the drip lines and a wetter area around the drip lines. With a strategy that takes mostly you count on patience. And so in this case, these patterns took about 3 weeks to develop. With 10 days or 15 days, you can also create a larger wetting front, depending on how much crop water uptake you have at that moment in time. Is that a problem, that you keep these drier areas in your soil with these types of systems? We found that it doesn't matter for our alfalfa crop, simply because once the root system is established, it does intensify its root system and root network around the emitters and in the areas where most of the time wetting will occur under any type of irrigation event. So yes, your water distribution is variable, but so is your root water uptake distribution. So once you have your root distribution and your root network set, the fact that you don't wet up your entire profile with an individual event no longer matters. So that was kind of a neat finding. Then outdoors to Colehurst. This is a really nice field because when you start walking in the southeast corner and you follow the white line to the northwest, sort of just past the pivot point, you have to climb up 10 to 15 meters. So this is a field with a really great large elevation gradient. It has some soil texture variability, nothing crazy. It's mostly sandy loams and loams. And in the lower half, so in the south half of the field, there is a potential for temporary groundwater issues. There's saturation at the beginning of the growing season. Parts of the field are tile drained. There used to be wetlands in here that still show up every now and then if it's really, really wet. Now the question in this field is, we expect soil moisture differences, right? Are they stable in space and in time? So we survey this field along this transect, and we also install soil moisture sensors for prolonged periods of time. We have some groundwater stations at the south end, and we measure the weather. And so in 2018, we had sensors at two sites, one in the north, or the high half, and one in the south, or the low half. And soil moisture dynamics were pretty much what we expected. So in the top figure with the wriggly lines, that's at the lower location. So high water contents, fairly stable through time, a little bit of peaks in the shallow sensors. And in the north end, so the lower panel, we see a lot of variability, large drops, quick responses to irrigation, but in general, much, much drier. So total soil moisture in the root zone behaved perfectly according to that sort of that intuitive understanding of how a field with such an elevation gradient, how that should work. The south end, very wet, low responses, keeps on being wet throughout the season, and the north part, or the higher part of the field, drops significantly. Now, the owners of this field do some kind of precision irrigation. So they windshield wipe. So the top half of the field receives a lot more irrigation water than the south half. In 2018, it was about 50-50, or, well, there was, say, 100% of irrigation at the north half and about 50% at the lower half. In 2019, when they were growing spring wheat, they kept up that ratio, but the total soil moisture in the root zone was completely different. So if you compare the two orange lines, you now see that that north end, so the high and dry location, started off wetter than in 2018, and that the irrigation, they really went for it. So over the course of the season, that profile actually built up moisture. Whereas in the south half of the field, we started off drier than 2018, and because they now also skimped even further on the irrigation, all of a sudden it no longer behaved as if it were one big wet puddle. We see some real decreases there in response to crop water uptake. And at the end of the season, the north half, the high half, was actually wetter than the south half. So, room for improvement, but lots of management already being done. In terms of yield, in 2018, we did see a significant difference between the north and the south half, but in 2019, that was completely, that had completely disappeared. And according to the local agronomist, it also was a bumper crop. This is a field where we take our toys to because it's nice and large, and it has phenology differences that you can observe from a drone. So we were able to pick up on differences in timing of flowering, and on the one half, the crop, especially in 2018, grew about twice as tall as at the south half, which was kind of interesting to me. But in terms of water use, the differences aren't that big. So we flew a drone with a thermal camera. So that's the figure on your left. That captures a reflectance in the infrared spectrum with which you can determine the canopy temperature. And that canopy temperature can be translated into a measure of evaporation or evapotranspiration rate. So we can estimate how much water a crop is using at different moments of the day. Now in the morning, which are the two orange patches, there's differences in the field. So depending on sort of where the moisture is, the evapotranspiration switches on earlier or later. But halfway the day, those differences are completely gone. The bright green, sort of, yeah, hallucinating images, they're just one rate. It's completely uniform. Our newest study is a 4-year potato field study. in which we follow 5 different potato fields per year. And these fields are located in 3 irrigation districts. They cover a lot of topography and a lot of landscape types. So we have everything from razor blade flat almost to very hilly, again 15 meters of elevation difference, and stuff where you sort of, yeah, I don't even know how you call that. Soil texture-wise, there's everything from silty clay loam to sandy loam. And what we hope to do in this study is to find out where the sweet spot is between landscape and management. So imagine that there is an optimum way or balance between your input, your effort of managing your irrigation, and what you get out in terms of yield profit or water use efficiency gains. So if you have a very flat field, sandy loam everywhere, you probably don't have to put in much management effort in order to get a good water-based yield out of that field. You can probably do a soil moisture sample every week, and then apply the same amount of water in your entire field, and you'll probably get a good crop. So that's in the lower left corner of this figure. The more complex your field becomes, the hillier, the more variability you get in terms of soil texture, the more effort you'd have to put in order to get your optimal yield in the entire area of your field. And then we can probably also hit a level of complexity in the landscape where no matter what you do, you have a VRI pivot, you have a drone, you use satellite imagery, whatnot, even that is not going to bring you an even yield anywhere just because your landscape is not completely suitable. The goal of this project is to find, to find such a function, or to find the optimum shape of that relationship between landscape and management strategy or management needs. So we're in year 1, so not very far yet. But the way that we do that is by quantifying the landscape. So we measure the elevation, we map out what all the elevation differences are, we map out the distribution of soil texture in the field. We measure soil moisture dynamics at different locations in this field. We measure how much water the producer is using. Starting from next year, we'll be surveying the producers as well to sort of figure out how people make their irrigation decisions throughout the season. And then we try to come up with a measure of complexity. So one way of doing that would be to take the elevation map of a field and to see how far it deviates from the average. So these are 5 lines for 5 fields. And if a field is very flat, it would have one single peak right around the 0, because all elevations in the field would be fairly close to the average value. Now you can see already in this figure that there's lines that have multiple peaks that are almost flat, or something with a very high peak around -1 and then a second one around 0. So this is a way to capture the variability, in this case just of elevation, but this is a way to capture all the information in a map into one specific function. And if we start to rank properties in that field or happenings in that field by the complexity, so in this case the elevation, which goes from less to more complex, then we can start to rank outputs and see if there's a relationship. So in this case, we're looking at the yield of potatoes. If we go from a flat, less complex field to a more complex field, you see that the total yield and the marketable yield decrease, and that the variations around these numbers increase. And that makes sense, right? Because if you have a field where you have both a dry area and a wet patch that you have to manage while irrigating with your uniform irrigation material, you'll overwater at some points and you're underwater at other locations. So that's captured in this ranking of these yields. Now, we try to do the same for these soil moisture observations. That's a little bit trickier, because as you can see, when we show just the time series of a low complexity field and a high complexity field, then between points, it's kind of difficult to first of all, figure out what you're looking at, and second of all, to say how they are different. Especially, so these are 4 panels that represent different depths in the hill, just under the hill, and then 2 depths deeper under the hill, and then 5 observations from different locations in the field in each figure. So in the top, you see immediate responses to rainfall and irrigation, and the deeper you come, or the deeper down in the profile you go, the less responses you see to individual events. Someone just started new in our group, and he's going to pull apart the structural properties of these time series to see if we can quantify differences, not just by going crazy and sort of cross-eyed by looking at these figures, but to capture them in statistical numbers that can say, okay, well, these lines may have different averages, but they behave the same in response to an irrigation event. Ongoing work. Hopefully next year I could show you something more tangible about that. So, the takeaway. Precision irrigation requires monitoring and an understanding of the why of variability, and maybe also an understanding of how much variability we have. There is room to do more with less water, and these are exciting times. This is very much a team effort, and I would like to thank all the producers in this room that I work with, and hopefully there's more future collaborators in here as well. A special shout out also to the province team at the demo farm. Lethbridge College does not have their own research farm, but we use graciously the facilities at the province a lot, and hope to do so in the future as well. And one last piece of advertisement. Lethbridge College does more than just irrigation. We have a post-harvest storage lab. I forget the name of it, I'm sorry. But we do, we're trying to take everything from field to table and work on problems that occur along the entire value chain. So if you have any questions about that, please let me know, send me an email. Thank you.